And then one of the things in IR that's very popular is query performance prediction. So which is like trying to estimate the quality of a system. So the output of an IR system is a rank list of documents, as we know. So in this talk, we'll be talking about query performance prediction. That's more like an algorithm to estimate like how good is the retrieved quality of documents without essentially making use of the relevance assessments. So I'll come to that. So just to briefly, I mean, Madhushan already introduced me, but I am in the University of Glasgow in the IR group. So if you're interested, and if you were interested to work on IR, then specifically reach out to me. I'm sure we can find out some ways of collaborating and then publish some papers, some interesting papers in conferences like SIG-IR or other conferences. Okay. So firstly, I'm going to introduce like what is query performance prediction. And then I'm going to talk a bit about supervised query performance prediction. So QPP, let's call that QPP. So QPP is typically an unsupervised method, or it has been so for the last 10, 15 years. But now with the advent of supervised learning and deep learning in particular, people have tried to apply supervised learning for QPP as well. And then it has worked out quite well. So I'll be talking briefly about all those. I'll be talking about two specific models. So one is the one that was published in Wisdom last year, and the other in SIG-IR last year. So one essentially is, a kind of a data-driven approach, but it doesn't make use of BERT vectors. So it still makes use of the shallow word vectors. And the other one that's more kind of complex model because it makes use of transformers and BERT embedded vectors. And then I'll be talking about an ideal like evaluation framework for QPP. I'll be talking about the problems that are there in QPP evaluation. And I'll be highlighting on like how could you alleviate those. And I'll be discussing very briefly about an ongoing work that we plan or we submitted to Wisdom that was rejected, but then we need to recycle it to SIG-IR. So I'm not going to reveal much of that, but I'm just going to give you an idea just in 1 or 2 slides, like what is the work, what is the main idea or the outline of that work. And finally, we can have some discussion about like future of QPP as well. Like, can it be applied for some other tasks other than IR? So we can have some brief discussion on that. Okay. So QPP is essentially like, if we can read this quote here, so it essentially captures whatever is being said. If we could determine in advance which retrieval approach would work well for a given query, then hopefully selecting the appropriate retrieval method on a per query basis could improve the retrieval effectiveness significantly. So the idea is like not all retrieval systems are good for all types of queries, right? So maybe there are different types of retrieval models. I don't know if you're aware of them, but BM25 language model, and currently nowadays there are supervised models as well, like Colbert and BERT, cross-encoder, bi-encoder, DeepCT, and all these different methods are there, right? But it turns out that, I mean, so one of the things in IR that people usually do is per query analysis. And it turns out that not all systems are good for all types of queries. But if there was a way of knowing like which types of system is going to work well or is likely to work well for what type of queries, then essentially we could have a very optimal combination of different systems, right? And one more like motivation is like one of the things that usually works well in information retrieval is query expansion, because your query is not always well specified. So usually it's the case that if you expand your query automatically and include additional terms, you might actually improve your retrieval results. But again, not all queries perform well with query expansion. So the whole idea is like if there was a selective way of choosing the different steps in an IR pipeline, then probably we could get a more optimal way of like applying all those different steps in the pipeline. So that's why we're interested in this problem of QPP. We want to know, like with this method or with this retrieval model, with these choices in my model, how good am I doing? So that's also an estimate, but if the estimate is good enough, then that at least gives me a way of choosing the different steps in my pipeline for different types of queries. Okay, so that's the whole motivation of doing QPP. Okay, just to illustrate the idea visually. So let's say we have a query. Sorry, I wanted to highlight on this. Agoraphobia. So that's one query, and the other query is black bear attacks. Right now, which query do you think is better for a retrieval system to retrieve documents? I mean, what do you expect? I mean, let's say you retrieve top 10 documents, just the first search engine result page with Google. Which query do you think will give you or will fetch you more relevant documents? Is it this one? And why is that? Single word, so it's not just like the presence of one word, but that word is very specific, right? So you don't expect to see this word many times in the collection. So the inverse document frequency of this word is expected to be pretty high, right? Which means that it's relatively easier to filter out documents that has those words in respect to the other ones which don't have those words. And if it's the case that a document has that word, it's more likely that that document will be relevant for this query. It's very unlikely to found the counterexample, right? So if you have this word, usually that document will be relevant. So it's usually easier for the system in this case to retrieve relevant documents, right? And one more argument could be that you don't expect to see many relevant documents for this. I mean, there are supposedly less relevant documents that addresses this information need than with this one, because that's not a very specific query. Because when you look at this query, I'm not specifying the geographic region. I'm not specifying the year. So I might be interested in black bear attacks in 2022. I might be interested in, like, I don't know, in northern side of Europe, or maybe in Canada. I don't know. So these are all like underspecified expression of an information need, right? So it may turn out that if my information need was specific to certain location or certain time, then the other documents that the system retrieves won't be relevant for this query, right? So clearly information need is more specific in this case, and it's less specific in this case, right? So this is what we try to estimate, right? So there should be some characteristics in the query. Like one of the things we mentioned is the IDF of the terms. So even the average IDF of a term could be an indication that how likely it is for retrieval systems to retrieve relevant documents for that query. Similarly, there are other measures that we can look at. Okay. So yeah, the idea is like I have got many retrieval models like LMJM, LMDirichlet, BM25, and then the QPP estimator, what it does, it's also a system, it's also an automated algorithm, which basically takes input what? It takes input the query and the retrieved documents that I get with that query, right? It has to cook up some method of suggesting a score which is high if I believe that there are more relevant documents that I've been able to retrieve. Here, I means the information retrieval system, right? So given a system, so what are the inputs to a QPP estimator? So one of the inputs definitely is the query, right? The other input is the top retrieved documents that you get with that query. Let's say the top 50 or top 100, whatever, right? So with this query, you feed this query to this estimator, you feed in the top 100 documents to this estimator, and you feed in the name of the model, like what model was used, right? Sometimes even that's used in some cases, right? And then this method or this algorithm is going to come up with a score. And the higher the score is, the better is my belief that I have fetched more relevant documents for this query, right? So till now, is this clear to you? Okay, good. Yeah, so there are always a number of difficult queries for which we don't do quite well. So that's one of the reasons why we need QPP. And detecting hard or poor performing queries is useful because we can, like as I mentioned, we can have a different application of the pipelining steps that can be applied, right? So we could be applying query reformulation if we are predicting that we are not going to do well for this query, like for example, the black bear attacks. So maybe that's a candidate for query expansion, because I want to add like what part of the world am I interested in black bear attacks, right? So that could be like specifying my information need more, and could be guiding my query expression towards a very specific expression of the information need. Feedback to the system, similarly, query formulation, and you might employ something like query expansion, relevance feedback to improve your results. Reformulation of queries is something that the system can guide you, right? System can say, okay, did you mean this or did you mean that, right? So you type in your query, but it can provide suggestions for improving your query or reformulating your query. And query routing as well. So if you have got multiple retrieval systems, like which retrieval system do you want to make use of for this particular query? Okay. And predicting the quality of retrieved documents to satisfy the information needs behind the query. Yes, so that's what we do. So types of QPP estimators. So one very simple way of coming up with an estimate is just use the query and nothing else. So don't use the top retrieved documents at all. Just use the query features, and you could get some score based on that. Let's say, for example, the average IDF values of the constituent terms in a query. You can use that, or you can use the max IDF. Now, what's the problem with this approach? So it's completely model agnostic, right? And you'll get the same estimates for every model. So BM25, language model, DeepCT, Colbert, they will all give you the same estimate. Why? Because the query is the same, right? The average IDF for that query is the same. Agoraphobia, it's the same query. It's the same value that we'll get for BM25 and language model, which is not good, because clearly the retrieve lists are different or can be different. So we want to have different estimates for different models. If we're not doing that, then the routing thing that we talked about, like we want to choose the best retrieval model for a particular type of query, that's not going to work, right? So usually this is very limited, right? So you want to enhance this with post-retrieval based estimate, which again, it takes as input the retrieve list of documents as well, right? So the function, the QPP estimate function, depends on the query features and also on the document features, right? Okay. And then there are some usually, some well-known approaches like Clarity, WIG, and QC. I don't think I'll have time to delve into all those in details, but just to give an idea. So the idea is like in Clarity, you need to check, like if you are doing this analysis on the top 100 documents, you need to see like how good is the top 10 or how distinctive is the top 10 from the rest of the bottom 90, right? So if the ones at the very top are very distinct from the ones that are not at the very top, right? This indicates that you have been able to filter out the very top from the rest quite effectively. And the clarity score in that case will be high. A similar idea is also used for NQC as well, right? So all these methods, they kind of use very similar heuristics to come up with the scores. Okay. And there are robustness-based approaches, which reformulate the query automatically. So you have given a particular query as input, but then I could reformulate that query internally, and then I could come up with different rank lists. And then I could analyze like how robust is my retrieve list of documents, right? So that could be an indicator. Yes.
Suppose you know you've heard of a song, you don't know the name, but you know a phrase in the lyrics. Okay, and you do the Google search just based on the lyrics. Now Google tries to go through the document which song does it belong to. So then it has to again use some sort of clarity-based approach, because it's just a song. It has to understand. It has to sort of parse the entire document.
Oh, but that's a part of the retrieval model, isn't it? If you have a query, if you want to get a rank list of like documents in this case or songs in this case. Yeah, that's true. That's true. But whatever you're saying, that will be a part of the retrieval model. I mean, you want to improve retrieval model for songs retrieval or for lyrics retrieval, but that goes into the paradigm of the retrieval model itself, right? Because that's the output from a retrieval model. You want to sort whatever your items, like in this case, your songs, based on maybe in this case that there could be some signals from your documents that you are looking for. And then so that's not a part of the QPP, right? So that will be a part of the retrieval model. So QPP has got nothing to do with retrieval. Given a retrieve list, you want to estimate like how good is the retrieval list, right? Yes. Uh-huh. Yes. Exactly. To see like how many relevant documents have been able to retrieve, right? But then even then, yeah. So even then, so that's where the application of QPP stops, right? So when you predict that how likely is it that I have done well for this query, the output or the scope of QPP stops right over there. The next step is essentially a part of retrieval model, right? So maybe I could be using QPP in my retrieval model. Okay, so maybe I do a first step retrieval, I do some analysis, and then I do a second step retrieval. But that's the whole, like that whole system is a retrieval model under which there is a small component for the QPP, right? So QPP essentially analyzes like how good is the retrieved quality. It won't actually go and retrieve documents for you, right? So that will be the scope of the retrieval model. Okay. Yeah, but the whole idea is like you could use this to improve your search. Yes. That's definitely, that's true. Yes. Yeah. Uh-huh.
What I know about the retrieval system, what they do is they use kind of feedback from the user, like which results.
Right.
So if you want to also do something similar here.
No, I mean, if you get true user feedback, that will be true relevance feedback, right? But that's very unrealistic to happen in practice because users are not keen to like, you can use click through rate on everything, but then that doesn't really, yeah. Yeah. For the unsupervised approaches, it's simply some heuristics that we apply, like the collection statistics of query terms and the scores, like how distributed are the scores and all this, right? So how significantly different is the top 5 scores from the bottom 50 scores, something like that. So these are statistical measures, and then just some estimates. So it works in certain cases, it doesn't work in certain cases. Yeah, the unsupervised ones are essentially statistical heuristics, nothing else. Yeah, so UEF, it's basically, if you apply feedback and then come up with multiple retrieve lists, and then you can look into like how robust are those lists themselves, which gives an idea about like how robust or how good was the initial query itself, or how good is the initial list retrieved for the query itself. Okay. Now we can briefly talk about, so till now, we know that, okay, so we get some estimate and then that's all fine, but we need to see how good we are doing, right? Just like we do for standard IR pipeline, we get a list of documents, but then we need to compute something. So we compute, let's say, precision at 10 or whatever, average precision or NDCG, using a set of ground truth relevant documents, right? So we know that this is my benchmark set of queries, and I know that these are the relevant documents that should be retrieved for those queries, right? So there's a ground truth for that, which gives me the ability to compute a metric to evaluate between retrieval systems. So if I have system 1, BM25, I have system 2, language model, I can compute mean average precision for those 2 models, and then can I argue that BM25 is better than language model, because map of BM25 is 0.25, whereas map of LM is 0.24. So we can do this kind of comparisons, right? So what do we do for QPP? Let's say we have got 5 different QPP systems. So we have looked into some of them, like say Clarity and NQC, WIG and UEF, and let's say average IDF, max IDF. Which one is the best? How do we measure that which QPP approach is better? So we need some kind of ground truth, and we need some way of defining a metric, right? Now, what do you think can be done. So we have the query, the retrieval model, we get documents, and then so we can compute the AP, the average precision, right? Because we know which documents are relevant, right? So just like we evaluate higher systems where we know that for this query, what is my set of relevant documents? So I can clearly check that, okay, so this one is not relevant, this one is relevant, this one is not relevant, this one is relevant, and so on, right? And then I can compute AP value for this particular query, okay? Now here, we cannot evaluate only on one single query. We need a benchmark set of queries, right? So let's say we have got 50 queries. So for 50 queries, we'll compute the AP values, right? So we'll have 50 different sets of AP values, okay? And I can sort the queries based on the AP values. The one right at the top, let's say we sort that by decreasing order. The one right at the top, what do you think that indicates? That indicates the easiest query, right? Because the retrieval system was working the best for that query, it gave us the highest AP value, right? So if we fix the retrieval model to BM25, and if we sort my 50 queries based on the AP values, the one at the very top, let's say 0.9 or something, that I know is the best performing query. So my retrieval model BM25 performed the best for that query. So I have this, let's call that ground truth set or ground truth list of queries, okay? And with my QPP then, for all those 50 queries, I find out the QPP scores for those queries, right? Again, a high score indicates what? An easier query, right? So again, I can sort these queries based on my estimated scores, right? And then I can compute a rank correlation. Okay, so if my rank correlation is perfect, then my QPP system is perfect. If my rank correlation is very low, which means that I have like predicted reverse order, which means that my QPP method is not good, right? Because for the queries where we actually get a high AP, I have predicted that query very down below in my list. So the estimated score for QPP for a high AP query, if that's low, that's not a good thing, right? So I want, if this is to be high, then these scores are also to be high. And if these are low, then my scores will also be low. Okay, so usually we compute rank correlation this way. I mean, there are standard rank correlation measures like Kendall-Stau or Spearman's rank correlation coefficient, or you could even compute Pearson's. Even Pearson's is fine because that's not a rank correlation coefficient, but still, it has this correlation thing that if a value is high, this value should also be high and so on, right? So that's what we do. Okay, so let's talk a bit about some of the methods. Supervised models. I have to be aware of the time. What's the time? Okay, I need to finish quickly. Yes. Usually it's like people usually use Pearson's and Kendall's because Spearman's and Kendall's are pretty much the same. So usually you try out with two different metrics. I mean, one, Pearson's is quite standard. Yeah. Kendall's is like ordinal. Yeah. But even then, I mean, Pearson's also makes sense. I mean, it's not a rank correlation coefficient, but still, I mean.
That is not satisfy some of the requirements, but that is not
we as, I mean, empirical researchers, we are not statisticians, right? So.
The length has to be equal, I guess.
Yes, in Kendall's. So in Kendall's, the item set has to be the same. The item set cannot be different. Yes, cardinality has to be the same, and the item set, in this case, the item set is the queries, right? So the query set is the same. But let's say you cannot do that for two retrieved list of documents because one of the lists could be containing some documents not in the other list, right? So in that case, you cannot compute Kendall's. So then there are other measures that people usually use, like rank biased overlap. So the RBO. So yeah, in this case, you don't need RBO because it's the same items, right? Okay, anyway. So this is the wisdom paper that was published this year, or the last year, actually. We are in 2023 now. So this is a data-driven approach. So this work was done by my PhD student, Kuchana Datto, and her supervisor, Derek Green, with me as a co-supervisor as well, and Mondada from ISI. Okay, so this was an extension, so as to say, of this work, which used essentially features for QPP. And one of the things that this paper did was it involved application of different QPP methods like UEF or NQC or Clarity. So the idea was like, if you have all these different estimators, you want to combine with a neural network, you want to learn the optimal parameters of combining or coming up with an optimum ensemble, right? So that was the idea of this paper. So it essentially was trying to find an optimal ensemble, but then the limitation was that you still need to rely on those estimates, right? So I need to have my QPP scores from NQC, from WIG, from Clarity, and whatever, in order to find the optimal combination. So the model was using data, three different types of data. One was retrieval scores themselves. The other one was a term distribution analyzer. Essentially, it's the term document matrix, right? So it's this documents here and then terms here. So it's this big document term matrix restricted to only the top 100 documents or top K documents, let's say. And additionally, it also used the word embedding vectors as well. So these three types of inputs were fed to the model, and it was trained on data. So in this case, how could you train such a model? So you need to have pairwise examples of queries, and you need to know that, okay, so for this query, my retrieval system is doing well, and then for this query, it's not doing well, right? So if you have pairwise examples of these kinds, where you know that, okay, so for QA and QB, it's either AP of QA is higher than that of QB, or it's the other way around. So it has to be a binary decision, right? It cannot be anything else. So then you could train a binary classifier, with these as inputs, and then with pairwise data, and then you could train such a model, right? And then in the test case, you haven't seen those queries, but then you have the model trained. And essentially, the belief is that, if you get similar terms or if you get similar distribution of terms, then usually the model will be able to predict like which query is more difficult, right? Okay. So in our model, so as I said, like this model needed to rely on the existence of the different QPP estimates to be able to find the optimal combination, but we don't need that. So ours is entirely data-driven, and we don't need the existence of any existing QPP estimates. So let's see how we do that. So usually models, you can classify models in two different types. One is the late interaction, the other is the early interaction, right? So early interaction, or let's talk about late interaction models first. So late interaction models are usually of this kind, where they will typically have shared parameters here, and Siamese type of model where you basically learn some representation of the input, and then at some later stage, you merge the two representations, right? And then you have like another set of dense layers and to learn. And then you train the network with, in this case, binary labels, right? So that's how a late interaction network works, like a Siamese network. But usually it takes like more time to train such networks. And then in our case, it's difficult to. So it's not just the queries that we need to feed in, but it's also the top documents that we need to feed in. And then that's difficult in this kind of situation, right? So what we did was we took resource to this type of an architecture where, it's early interaction. So basically you convert a pair into an instance, right? So in this case, let's say I've got two different queries, QA and QB. Somehow you compute the interaction between them, and then you transform that into a matrix or a vector, and then that is your input, right? So your input is, you convert a pair into one single instance, and then you learn a set of parameters, right? So it doesn't involve shared parameters like the late interaction model, right? It just involves one set of parameters. So you compute something from the data from the pair, and then you just have a multi-layer perceptron or layers of like parameters that you train on top of that. Okay. Okay. So in this case, we want to take into account the documents that we retrieved, right? So on one side, we have the top documents retrieved. On one side, we have the query. We can compute some kind of an interaction, and what interaction could that be? So I could take the document terms, I could take the query terms, let them be word embedded vectors, and I could simply compute an interaction between the vectors themselves, right? So I can compute how similar are the two vectors, right? And then I could quantize that into an interval, because I know that everything has to be between -1 and +1. All the cosine similarity values between two word vectors are bounded, and this range -1 to +1, I can discretize that into fixed length intervals, right? And then, which means that for every interaction between pairs of terms, I get a fixed length vector. Okay. And then let's say if I've got, so I can have bounds on the queries and my documents. I know that, okay, so query, the max query terms could be like 10 or 15, whatever, right? So I could have a max number for this. I could even have max numbers for these documents, which means that I get essentially a tensor, right? So I get interaction vector, let's say of length b, because I could discretize -1 to +1 into b intervals. And for every interaction between every pair of terms from queries and documents, I get a b length vector. And then I also know that I could get k times, because if k is my maximum number of query terms, I could get k times that. And if I've got m documents, I've got m times k times p length vector, right? So it's a tensor, then we could reshape that into a matrix, and then we could have like sets of parameters, and then we train it on, as I said, on pairs of queries, where I know that it has to be a binary decision, okay? So this is the basic essence of the model. And if you want to get into specific details, we apply 2D convolution here, and then you have max pooling, and then usual standard stuff, right? So one thing to notice here is that, okay, so we train the model in a pairwise manner because we have this sigmoid layer here, and then it is either a 0 or 1 in the ground truth, and when we train the model, the values that we predict from here, y hats, these are sigmoid probabilities, right? Now, during the testing time, there are two ways in which you can test this model. Either you can use the whole model and then feed in pairs of queries, which is a bit difficult thing to do, because then you need to form all these pairs, and then somehow from the pairs, you need to again get back to the scores. An easier way is to just throw away one part of the model, because it's shared parameters, right? So throw away one part, just use one of these parts, and then just feed in one query, right? And you get back some score from here, okay? And then you can directly use that score as your QPP estimate score, okay? Okay, so these are all like pretty standard stuff, so I'm not going into all this. So if you want to play around with the code is available on Git, and then you could play around with it if you want. I can quickly go through some results. I don't have time to go through all this. Usually it's the case that, okay, so we have the baselines for the unsupervised ones, clarity and QC and everything. We had this weakly supervised neural QPP that relied on this optimal combination of the estimates. And then with our method, it's clearly outperforming all these ones, right? So we get quite a significant jump, let's say, from NQC, which was giving 0.6720. Let's not look into accuracy. Let's look into Pearson's or Kendall's tau, right? So 0.4041 here, compare that to 0.5434. So that's a very, very high jump. A part of that has to do with the supervised training, because even with this supervision, we get 0.5090, which is a big jump. But from 0.50 we get to 0.54, which is also a significant jump as well. Okay. So yeah, let's skip all this. Okay, so another paper that we got published was the Sigayer paper. Okay, still have some time. Which was an improvement on this paper because firstly it uses transformers and secondly it uses the positions of documents. I'm going to talk about that. Okay, yes. Okay, maybe it's better if I can show you the diagram. Okay. So the idea is like, okay, so we have got top 100 documents, let's say, for example, right? So one of the things we didn't do in the wisdom paper was like, we treated document 1 and document 5 in the same manner, right? So which is not good. You need to somehow consider the positions of documents, okay? So one way of doing that would be to use the positional embeddings in BERT, and you could just use the rank values to learn those, right? So we fed in the rank values of the documents. One of the things that you need to do is like, if you want to model a sequence of length 100, that's not a good thing to do, okay? Because it's a long length sequence and your parameter convergence could be slow, okay? So one of the things that we did was like we broken that or decomposed that into chunks, and then we have a sequence of chunks, right? Which is easier to handle. So a chunk length could be of 5 or 10, but then if you have top 100, if you're considering top 100 documents, then you'll have, and the chunk size is 10, then you'll have 10 chunks, which is easier to manage, right? So the idea is something similar to hierarchical LSTMs, right? Where we, like, if you have long documents, we don't just have one layer of LSTMs because, it's problematic to converge. Whereas if you have a hierarchical LSTM, usually it gives you better results, okay? Okay, so that's what we do. The idea is pretty clear. We have these LSTMs here, right? So we have the BERT vectors for each chunk, and then we have an LSTM layer which takes into account the sequence of those chunks. And finally, that fits into, and similarly, a softmax. So in this case, it's not a binary prediction. In this case, we predict how many relevant documents are there in this chunk, right? So in that is a number between 0 and P. Okay, so it's a P plus one-dimensional softmax. If your chunk size is P, you could have the case that no document is relevant, so that's 0 relevance, and you could have the case that all of them are relevant. So you have got P plus 1 numbers. So that's why it's a P plus one-dimensional softmax. Okay. Okay, and then finally we compute the weighted average. So rank embeddings, that was one way of doing with the different positions of documents, and even this one. Because if you're predicting that, okay, so you're right at the top, let's say a chunk of length 5 that has got 3 documents that are relevant, and the one at the bottom, let's say, the 4th chunk, which is from ranks 15 to 20, let's say that has got 3 documents, relevant documents. They're not equal, right? The one at the very top, you have to consider that to be more important. So that's what we do here. So we compute a weighted average, weighted by the positions of the chunks, or the reciprocals of the positions of the chunks, right? So which puts the highest importance to the first chunk in my list of chunks, okay? Okay, so again, the code is available. You can play around with the code. Yes, yes. Yes, so that's a very good question. You usually need large amounts of data to train these models. Even if you have, like, I don't know, if you have got 100 queries, you could use a part of that as your training set. Let's say use 80% of queries for your training, which means that you'll have like not many to train on, but at least 80 queries. But that's not that, it's not going to give you good results. So what we did was, the one good thing with MS Marco is that it usually has lots of queries. One of the problems is that the relevant documents, they are not rel judged in the usual sense. They are not assessed manually. They are usually obtained by, they control some user studies, and basically it's the clicks that are saved. So some questions were asked, and then the participants, they bookmarked some of the passages, and those are treated as relevant documents. But the good thing is that there are loads and loads of queries. So if I remember correctly, the training set has something like 800,000, Madhusudan, do you remember? 800,000 queries, right? Yeah, we don't remember, but there are lots of queries to try on. So we used it, MS Marco, although they are not, as I said, not manually well judged, but still. And we tested this on manually well judged set of queries. In MS Marco, it uses the same collection. It's called the TREC-DL, TREC Deep Learning Task. 2019 and 20, they have 43 and 53 queries, or 54 queries. So there are like significant number of queries you can test, but the training was done on MS Marco. Okay. So these details are there in the paper, so you can just go through it. Okay, again, so we tried out different ablations as well. Like if you leave out the sequence information, if you leave out the chunk information, if you leave out the rank embeddings. So it turns out that you get a decrease in the results. And if you include everything, then you get the best results. So which means that all these are important pieces of information that the model uses to estimate effectively the QPP scores. Okay. Okay, now I think I can quickly go through this as well. Okay. Okay, so we looked at this evaluation workflow for QPP. Now there are some problems with this, which I want to highlight. So this was published in ECI last year. So this work is a bit different from the other ones because this is not about coming up with a new QPP method, but this is coming up with a new way of evaluating QPP systems, right? So the idea is, or what we wanted to propose here is, like, we have been evaluating QPP not in the right manner for all these years. And I'll be quickly saying why, okay? Okay, so one of the things that you realize is, yes. Query and the retrieval model also, because you have the top documents retrieved.
Yeah, I mean that queries are okay because you're taking the correlation of the two days. But then your model is involved. You're assuming that your model is possible. Absolutely correct.
No, not really. No, why?
I mean, is QPP a function of the query and the model, or only the query?
QPP is a function of both the query and the retrieved list of documents. Not the model directly, but the retrieved list of documents, which is obtained from that model. So it's a function of the list. So indirectly, it's a function of the model also, right? With respect to a model, yes, yes, yes. And so it's not just the model, but one thing I want to highlight here, if you remember the way we evaluate QPP, there also has to be a target metric, right? Because we talked about, so let's again go back to this figure, right? So we talked about measuring AP or NDCG or recall or whatever precision. But then this list can be different, right? I mean, if I sort my queries based on recall, then this list is different. If I sort this list based on AP, then this list is different. So I could be having like Q1, Q5, Q3, if I sort them by AP, whereas Q3, Q5, Q1, if I sort them by recall. So it depends, the evaluation depends on the metric here as well. But a QPP method is oblivious of any retrieval metric, right? So I just want to predict like how good is my retrieve list. I'm not going to predict in terms of recall or in terms of precision at K, in terms of AP, I don't know, right? So nothing of that sort is a part of the QPP system. But when you are evaluating QPP systems, you are inevitably people use AP, they don't use the other ones, but it can turn out. So that's something that we wanted to investigate, that if you replace AP with something else, a different target metric, let's say, we had evaluated that NQC was better than clarity, if we had AP, but what if it's the other way around, right? So these things then won't be a good thing to observe, because that would mean that your evaluation is very much dependent or very much sensitive on the choice of the metric, right? And of the model also. Because, if I change BM25 with language model, then that could also have an effect on the relative rankings of my QPP systems, okay? So I would no longer be able to tell that NQC is better than WIG for everything, right? So it has to be a very specific set of choices for which I would be able to tell that NQC is better than the baselines. Okay, but this is something that people usually ignore or have ignored for all these years in QPP evaluation. Okay, and this is something that we pointed out in the paper in ACIR, that this is something that you should be doing, specifying the configuration of a QPP experiment, right? Because it depends on the target metric that's being used and the retrieval model that's being used. Okay. Okay, so that's the idea basically. Okay. Yeah. So one of the research questions was like, what kind of differences do you observe, when you have these different configuration choices? Okay. So one with respect to the absolute values themselves, and the other with respect to relative rankings of the QPP systems. Okay. Okay, so let's look at the first set of results, where we look into that absolute values of the QPP scores, right? So this is the Kendall stove. Let's say we're evaluating that with Kendall stove. I don't know what was used, but let's say Kendall stove. So BM25 on AP. So if I am fixing a retrieval model, let's say BM25, I am fixing a target metric, let's say AP, right? I'm getting Kendall stove to be 0.5006. Okay. Now, what happens if I change that to NDCG? Okay, I get something different, 0.4879. And I could measure the standard deviation of these values, right? One of the things that you see here is like, if I change it to P at 10, my number goes down to 0.2525. So Kendall stove from 0.5, it drops to 0.25. It's a half of that value, right? Which is not a good thing to see. So if you measure the standard deviations across all these rows and all these columns, for some of them, you can really see some very high deviations, which is something that we want to avoid, right? Which is not a good thing to see. So in this case, BM25 shows us that it has got a very high standard deviation. In this case, AP shows us that it's got a very high standard deviation across models. So you could compute it across metrics or across models, right? In both the cases, we see like very high, sometimes quite high standard deviations. Okay. Okay, I can skip through all that. And then for some cases, we see lower deviations, which are like preferable, more preferable, right? So the idea is that maybe you should stick to those configuration choices. Okay. And in this case, you want to measure the relative changes in the QPP system's orderings, right? So if I've got, let's say, 10 different QPP models, I can rank them by Kendall stove. So I am saying that NQC is better than WIG, is better than UEF, is better than average IDF. So I have relative rank of my QPP systems, right? How consistent is that order with respect to my choices in my target metric and retrieval models? So that's something that we investigated here. So here, what you are doing is, okay, so I've, let's say LM, right? So LM, you fix one of the metrics, right? So it's some kind of a contingency that you have to measure. So let's say you fix that to AP at 10, and then you, on the other side, if you vary that to AP at 100, if you change that to AP at 100, if you change that to AP at 1000, if you change that to recall at 10, what happens, right? So in this case, an interesting observation is that, okay, so if I had used AP at 10, and if I change that to recall at 1000, my Kendall stove of the relative orderings of the QPP systems goes to minus 0.1429. So which means that if I had an ordering of, say, NQC, WIG, whatever ordering was there, the list is almost reversed in this case, which is not a good thing. Okay. So yeah, I mean, the whole table basically suggests that for some you will see very high values. One perfect correlations, right? AP at 100 with recall at 10. For some reason, it's like there is no change in the relative ordering of the QPP systems. So this indicates very unstable and very what should I say? Yeah, unstable results. And some configurations are stable, some configurations are not. Okay. And similarly, we can vary the matrix as well and then look at the results. Okay, so I don't think I will be covering that much. Okay, I'm just going to finish with this, just one slide for this, I think. Yeah. So till now we had looked at QPP systems that are trained in a supervised manner, like two models we had looked at. And then we had looked at the relative stability of QPP measures across variations in target metrics and models. So this work is a bit different because in this work, we wanted to apply the output of a QPP to improve retrieval. Okay, some of the ideas that we have been talking about, like, okay, so you predict a QPP score, but then what do you do with it, right? We all know that QPP is an essential part of retrieval model, but surprisingly, there has been no or very little work that has actually showed that, okay, so you can apply QPP to improve on retrieval, surprisingly. So this work was an attempt to do something in that direction. So the whole idea is like, okay, so let's say you have got a very simple example, right? So you've got a query, and then there are two choices in your retrieval model. Either you use relevance feedback or you don't, okay? And usually it's the case that if you do a per query analysis, you'll see that almost half the queries, they don't improve if we apply relevance feedback. If we use query expansion, almost for half of the cases, the results will be, the AP value will go down if we apply relevance feedback. So on an average, you see improvements because for some queries where the AP value was very low, it significantly goes higher up. But if you count like how many cases it actually goes down, that is a significantly high number. So let's say we have this choice, and then I want to selectively apply if I want to apply relevance feedback or not. So a QPP score could be an indication of that, right? So this could be a downstream way of evaluating a QPP system. If I have NQC and if I show that, okay, so if I rely on NQC, and then a very simple approach could be set some threshold, and then if it's higher than the threshold, you apply feedback, else you don't. So NQC could give you some value, whereas WIG could give you some value, right? And then that could be a way of evaluating like what is the actual downstream performance of a QPP method. In this case, what we do is we also want to train this, right? So let's say we have a simple pipeline where we have relevance feedback applied or not. So we have either the expanded query or we have the original query. And let's say we can train a network where we have these two lists, right? So we have got the list from the original query, and we have got list from the expanded query. Where is it? This one. This one. Okay, so we can pass that through a trainable model, right? So we can encode this representation in some way. Let's say with the interaction matrix that we talked about in our wisdom paper, or with the BERT-based encoding that we talked about in the Sigayer paper. So we could encode all of that and then have a feed-forward network. And then we could again like see which query improved and which query didn't. Okay, so during the training time, I know the relevant documents. I can compute the AP values, and I can see that for this query, if I apply relevance feedback, then my AP goes down. And for this query, if I apply relevance feedback, my AP goes up. So I have training data like this, right? So I could train a model which essentially learns whether to apply relevance feedback or not. Okay, so that was the whole idea. Yeah, so this is still like we are working on this paper, and we want to send this to Sigayer. Okay. So let's say, so summary, we have talked about QPP experiments, sensitivity of QPP experiments. We have talked about two different models. We have talked about downstream evaluation of QPP. So what are the future directions? Like, what can we do in future? So QPP provides an estimate about the quality of a model's prediction. It can be used for recommender systems because the output is a rank list of top key items queried to context of user, right? So this is quite standard. I mean, there is no brainer for this. So whatever we have done can also be done for recommender systems. Okay. This is a bit tricky. Can also be used for other prediction systems. Let's say you have got a classifier, a standard classifier, right? We want to see. So maybe it's so for some data instances, maybe it does well. For some other instances, it doesn't, right? Can we use something like a QPP, maybe a supervised technique or unsupervised technique, to help me choose the data on which I'll be feeling more confident? The classifier will be feeling more confident, right? Although there are Bayesian approaches which does this, but then having a relook at the QPP from the IL literature could also open up some avenues on this particular problem, right? And one of the things that I want to do is applying QPP on sessions of queries, right? Usually it's not just one query when we search. We have something that we want to look for, and usually it's a sequence of queries that gets executed in a search session, right? Some of them can be related, some of them can be a bit different, but I could kind of try to see how good my retrieval system has done for an entire session of queries and not just one query. Okay. So how to evaluate those, how to come up with QPP methods that is aware of the previous queries that were being typed, that were being executed, is something of a challenge. And that's something that we can work on in future. Okay, so with that, I think I can stop. And if you have any questions, I'd be happy to answer. Thank you.